What truly happens when a simple lawnmower engine and a plywood frame can cripple a multi-million-dollar air defense system? Welcome to Weapon Science. Today, we're dissecting an economic anomaly, the Shahed 136. This isn't about high-tech sophistication. It's about a brutal, affordable calculation of destruction. How did Iran transform off-the-shelf GPS components into a geopolitical nightmare? We'll peel back the layers of the Shahed 136 to reveal a terrifying engineering trade-off: consumer electronics defying high-end military interception logic. By analyzing its low-precision avionics, we'll see how crude engineering actually creates an expensive defense crisis, forcing modern militaries to waste their best missiles on mass-produced targets. Modern warfare is experiencing a systemic disruption, and the cause is this $20,000 flying object. We're mapping how Iranian engineers use cheap components to penetrate the world's most advanced radar shields. Why do high-tech missiles fail to stop this low-tech threat? The answer lies in the mathematics of attrition, not aerodynamic superiority. Let's begin our virtual dissection from its heart, the Mato MD 550 engine. If it sounds familiar, it's because it's essentially a modified lawnmower engine or scooter motor. This is a 4-cylinder 2-stroke piston engine. Very noisy, vibrates heavily, and completely lacks heat signature suppression or stealth features. However, this simplicity is a tactical choice, not merely a budgetary limitation. This engine is easy to produce in non-industrial workshops, its parts are available on the global civilian market, and its fuel consumption is very efficient for a one-way trip. No complex jet turbines, no rare metal alloys. The vibrations from this engine are so strong they can shake solder off ordinary circuit boards. This is why we see abundant use of industrial-grade epoxy glue throughout its internal parts. This isn't neat work, it's a survival technique to ensure the drone doesn't self-destruct before reaching its target. Moving to the airframe, or plywood exoskeleton. Most of this delta wing structure is made of a carbon fiber-clad honeycomb structure in plywood. These materials are transparent to certain radar wavelengths. To defense radar, it looks more like a large bird than a metal fighter jet. The use of these non-metallic materials drastically reduces the radar cross-section. Radar bounces off metal but tends to penetrate or be absorbed by plastic and wood composites. This makes the Shahed 136 very difficult to detect at long ranges, especially when flying low, hugging the Earth's contours. The delta wing design, integrated with the body, provides significant lift and enough stability for long-range, low-speed flight without complex ailerons. It uses simple elevons to control pitch and roll. Every eliminated part reduces cost and failure points. Notice the absence of landing gear. The Shahed 136 is launched from a rack using a booster rocket, which is then discarded. It's not designed to land. Eliminating the landing gear system and parachute mechanism saves significant weight, which is then allocated to a 40 to 50 kilograms warhead. Now we get to the consumer silicon brain. If you disassemble the Shahed's navigation console, you'll find the same chips as in your smartphone or smartwatch. Commercial-grade FPGAs from American or Asian companies, acquired through black markets or shell corporations. It doesn't use expensive, high-security military guidance systems. Instead, it relies on high-end civilian GNSS antennas. It can simultaneously receive signals from American GPS, Russian GLONASS, European Galileo, and Chinese Beidou. This redundancy is key to its resilience. What happens if the enemy jams or scrambles GPS signals? This is where cheap ingenuity comes in. A simple CRPA antenna is used to block interference signals from the ground, listening only to satellites from the sky, a physical solution to an electronic problem. And if all satellite signals are lost, the drone doesn't fall. It switches to a basic inertial measurement unit. Imagine this as the human inner ear that maintains balance. Although not accurate for long distances, the IMU is sufficient to keep the drone flying straight in blind mode until GPS signals recover. Iranian engineers often take open-source code from hobby drone communities and modify it. They don't write operating systems from scratch. They take what already works for drone racing communities and then add suicide mission parameters. Brutal development efficiency. Let's talk numbers, because this is where wars are won or lost. One Shahed 136 unit is estimated to cost between $20,000 and $50,000 USD to produce. Compare that to interceptor missiles like NASAMS or IRIS, which can cost $500,000 to $2 million per shot. This is the definition of cost asymmetry. If you shoot down a $20,000 drone with a $1 million missile, tactically you win, but economically you lose big. Iran forces its enemies into bankruptcy to protect their infrastructure. This is why they are launched in swarms. 5 or 6 drones are launched simultaneously. Air defenses might shoot down 4, but the 5th will get through, and the cost of shooting down those 4 drones has already depleted a weekly defense budget. Their targets are rarely purely military. They aim for power substations, fuel depots, and stationary civilian infrastructure. Damage to a multi-million-dollar electrical transformer, plus economic losses from power outages, makes the cost-benefit ratio of these attacks very high for the attacker. Sometimes Shaheeds don't even need to carry a warhead. They just need to fly to provoke enemy radar to turn on, revealing the position of valuable air defense batteries, which can then be attacked by more sophisticated missiles. They are deadly decoys. How does this slow, noisy object get through? The key is altitude. Shaheds are programmed to fly very low, often below 60 meters. At this altitude, the curvature of the earth and radar clutter from trees and buildings hide them. Although their sound is loud to human ears, like a motorcycle in the sky, for electronic sensors, it's not very helpful. Acoustic detectors struggle to pinpoint precise directions in noisy urban environments, and by the time you hear it, it's usually too late to react. Modern heat-seeking missiles are designed to lock onto the searing exhaust heat of jet engines. The Shaheed's small piston engine has a much smaller heat signature. Often, sophisticated missiles get confused and fail to lock onto such a cold target compared to the warm ground background. What we're seeing here isn't just an Iranian weapon, it's a global blueprint. This design teaches non-state actors worldwide that you don't need an aerospace industry to have an air force. You just need access to Alibaba, eBay, and a woodworking shop. This forces an evolution of defense. We're starting to see the return of World War II-style anti-aircraft weapons. Radar-controlled twin machine guns and the future of directed energy weapons or lasers. The only way to counter cheap weapons is with cheaper defenses. Back to the engine. The MD-550 is a reverse-engineered copy of the German Limbach L-550E engine, once used for civilian ultralight aircraft. Iran took the precise German design, discarded strict quality control standards, and mass-produced a good-enough version in China or locally. Its fuel system is very primitive. Fuel tanks are often just plastic containers shaped to fit inside wing cavities. There are no self-sealing fuel cells if hit. This means a single tracer round from a machine gun can set the entire drone ablaze in mid-air. Its pusher propeller is made of wood or simple composites, often 2 fixed-pitch blades. These are optimized for a single cruising speed of about 180 kilometers per hour. It can't speed up, it can't slow down, it's a slave to its own cruising efficiency. The launch mechanism is similar to a wine bottle rack on a truck. 5 drones are stacked. This allows for high mobility. The truck can stop, launch 5 drones in minutes, and leave before enemy counter-battery radar can detect the launch site. Often called a loitering munition, but the Shahed 136 is actually less smart than that. It doesn't have cameras or sensors to seek targets itself. It just flies to pre-programmed GPS coordinates. It's more of a propeller-driven cruise missile than a true hunter drone. The warhead is located right in the nose, often filled with fragmentation explosives to kill personnel or shape charges to penetrate armor. There are also reports of thermobaric modifications to destroy buildings. Its trigger is a simple contact fuse, hit, then explode. If you look at the wiring inside, it's a mess. There's no military-grade shielding against electromagnetic interference. These wires are similar to what you'd find in household appliances. This makes the drone vulnerable to high-power microwave weapons. The actuators that move the wings are standard servo motors you can buy at an RC hobby shop. Brands like HCH or their knockoffs, they're cheap but prone to jamming if exposed to dust or ice. Failure of one servo means the drone will fall spinning. Debris investigation shows components from over 30 different companies in America, Japan, Switzerland, and Taiwan. This isn't because these companies sold to Iran, but because third-party distributors and smuggling make export control of dual-use components almost impossible. Shaheeds are often launched at night. Why? Because visual air defenses can't see them. They rely entirely on radar, which, as we discussed, struggles to detect these plastic drones. Operators program flight paths over rivers or large highways. Rivers are natural, flat highways away from obstacles. Furthermore, radar often filters signals over water to reduce wave clutter, creating a blind spot for drones to slip through. Compare this to the American Switchblade 600 suicide drone. The Switchblade has advanced cameras, encrypted data links, and the ability to abort attacks. It's a scalpel. The Shahed is a blind sledgehammer. Switchblade is expensive and rare. Shahed is cheap and abundant. In Russia, the Shahed 136 was renamed Jiran 2. There are some local modifications, such as the use of more cold-resistant materials and improved quality of the Kometa GPS antenna, which is more jamming resistant. But its basic DNA remains the same, cheap and destructive. One of the Shahed's most effective natural enemies is the German-made Gepard anti-aircraft tank. Its short-range radar is accurate, and its twin cannons fire air-bursting shells. This is much cheaper than firing missiles, but its range is limited. Ukraine developed mobile fire groups, pickup trucks with heavy machine guns and searchlights. This is a low-tech solution to a low-tech problem: human eyes and bullets. Sometimes old solutions are the best for new problems. The sound of that lawnmower engine has a psychological effect. Hearing it buzzing over a city for hours creates terror. Civilians can't sleep. Sirens constantly wail. It's a weapon of terror as much as a kinetic weapon. Manufacturing quality varies greatly. Some drones are found with wood shavings still inside the fuel tank, causing engine blockages. Others have wires improperly soldered. Launch failure rates are estimated to be quite high, perhaps 15%. The delta wing shape and vertical wingtip strakes are designed so the drones can be neatly stacked on top of each other without wasting space. Shipping logistics become highly efficient. One standard shipping container can hold dozens of ready-to-assemble units. Despite abundant physical evidence, the politics of denial continue. However, serial numbers, welding methods, and specific components are indelible fingerprints. Forensic analysis of debris has linked these drones directly to specific factories in Iran. Many units are found using flight controllers available on AliExpress. Imagine the brain controlling this weapon of mass destruction could be bought by a teenager for a school project. This democratizes long-range strike capability to an alarming degree. So, up to this point, we've seen a paradox: a machine that is aerodynamically poor, noisy, slow, and cheaply made, yet successfully changes global defense strategy. It's not about being the best, it's about being good enough in large numbers. Its electrical system is powered by standard Li-ion batteries to power electronics before the engine generator takes over. These batteries are also vulnerable to extreme cold temperatures at altitude, which explains why attacks often decrease in intensity in severe winters. Although we call it a drone fun app, the use of carbon fiber on the outer skin is crucial. It provides structural rigidity without the weight of metal. The carbon fiber layup method is crude and manual, indicating a hand layup process, not autoclave. The Shahed doesn't fly in a straight line. It can be programmed with multiple waypoints. It can circle, change direction, approach targets from the rear or side to avoid known air defense zones. This path flexibility confuses radar predictors. Airspeed sensors or pitot tubes on Shaheds are often low quality. If these small holes are clogged with ice or insects, the flight computer can mistakenly think the drone is flying too slowly and command it to dive, causing a crash, a trivial yet fatal failure point. New factories are being built, including in Russian territory, with a target production of thousands of units per year. This industrial scale aims to overwhelm the production capacity of Western interceptor missiles, which are much slower and more complex. Caliber or Tomahawk cruise missiles carry 450 kilograms warheads, 10 times that of a Shahed. But a Shahed doesn't need to destroy a bunker, it just needs to burn an oil-filled transformer. For soft targets, the Shahed is a far more efficient solution. It's important to remember that the standard Shahed 136 does not have a Starlink terminal or two-way satellite communication. Once the launch button is pressed, there's no way to abort, change targets, or know if it succeeded until we see news on TV. The most deadly tactic is a mixed attack. Shahed drones sent first to overwhelm defense systems, followed by subsonic cruise missiles, and ending with hypersonic ballistic missiles. The Shahed is the opener for bigger killers. The air-cooled MD-550 engine has no fluid radiator. The air intake at the top rear doubles to cool the engine and feed the carburetor. This design reduces weight but makes the engine vulnerable to overheating in hot desert climates. Why does it sound so distinctive? The propeller tips move close to the speed of sound, creating mini shockwaves coupled with the absence of adequate muffler for weight saving. The result is a low-frequency hum that travels far. Warheads often use plastic explosives molded to fit the nose cone. This maximizes explosive density in limited space. Packaging efficiency is a recurring theme in Shahed design. Electronic warfare attempts to sever the drone's connection to satellites. Spoofing makes the drone think it's somewhere else, causing it to crash or fly aimlessly. However, the Shahed's anti-jamming antenna makes these efforts more difficult. Creative solutions like drone catching nets or even trained eagles are ineffective against the Shahed. Its size and speed are too great for small-scale anti-drone methods. We need kinetic force, bullets, or lasers. The next evolution is already here, the Shahed 238. This variant uses a microjet engine. It's much faster, but also hotter and much more expensive. This shifts the balance back towards high costs. The economic impact isn't just physical damage. Maritime shipping and air cargo insurance costs soar in drone-threatened regions. This uncertainty chokes the target country's economy without a single drone even hitting a target. There's speculation about adding cheap optical sensors for image-based navigation in the future. If drones could see landmarks and match them to internal maps, GPS jamming would become completely useless. The Shahed 136 proves that modern warfare is no longer just a contest of technology, it's a contest of economics. Built from cheap, widely available components, it can force opponents to spend millions defending against attacks that cost only a fraction of that amount. Technically, it's simple. Strategically, it's revolutionary. It exposes weaknesses in traditional defense systems and shows that sometimes quantity can rival quality. As AI, lasers, and autonomous weapons continue to evolve,